Okay, so you want to dive into this research paper from 1958, huh? 1958. Talk about a blast from the past. Clearly not afraid of a challenge, are you? The Perceptron. Let's unpack this bad boy. 1958. NASA was just getting started. Computers were like the size of a house. Can you imagine? Like, trying to figure out intelligence back then.
It's wild, right? What's so cool about this paper is that Rosenblatt, the guy who wrote it, wasn't just trying to build some fancy machine. He was trying to understand intelligence itself, like what makes us smart, whether we're talking about brains or these new computers.
It's like they were starting from scratch. Like, what did they even know about how brains work back then?
Well, sensory physiology, how our senses work, that was one area where scientists were making some headway. But the big questions, total mysteries, still kind of are in a lot of ways.
Okay, so like what mysteries are we talking about here?
So Rosenblatt, he hones in on three major questions. First off, how does our brain take in info from the world? Like, how do our eyes take light and make it into images? How do our ears take sound waves and turn them into, like, music? And then the real brain buster.
Yeah.
How is all that info actually stored up there?
Yeah, good question.
Right. Is it like a filing cabinet, like specific memories in specific folders? Or is it something more, I don't know, connected?
Oh, okay. So this is like the early days of thinking about how we store data now, right?
Right.
Like it's way more about connections and patterns than just like having things filed away neatly.
Exactly. And that's what Rosenblatt was thinking back in 58. He pointed out these two competing theories. One was this idea of memories as like coded representations, like little mental snapshots tucked away in the brain somewhere. But Rosenblatt, he was in the other camp, the one that saw the brain as this massive, intricate network where memories are formed by these connections between brain cells.
So instead of pulling out a specific memory file, it's like our brain is activating a whole network of connections to like recreate that memory.
Exactly. And that takes us to Rosenblatt's third big question. How do we actually use those stored memories, those connections, to understand the world around us, to recognize a familiar face or remember a song?
It's not just about storing data. It's about how we access it, how we learn from it. That's where the perceptron comes in, right?
Bingo. Rosenblatt believed that those connections, the ones formed through our experiences, actually become the way we understand and react to the world. Like the act of perceiving is the act of activating those specific pathways. It's all kind of intertwined,
Okay, my mind is officially a little blown. So how do you even begin to model that in 1958? What is a perceptron? Please don't tell me it's a computer the size of this room.
Well, it was a computer, but not quite room-sized, thankfully. Think of it more like a super simplified model of a tiny part of a brain. It's a system that learns to make decisions based on what it sees through this simulated retina, like a digital eye, sort of.
So is this like a really early attempt at teaching a computer to see?
Yeah, in a way, but instead of like showing it a picture of a cat, imagine teaching it to recognize the patterns of light that actually make up a cat's shape.
Okay.
That's closer to what Rosenblatt was going for.
Okay, I kind of get it, but how does it actually learn? Like what's going on inside this digital brain?
Now, this is where things get really cool. Remember those brain cell connections we were talking about? The perceptron has those too, but they're artificial. Rosenblatt called them synapses, and each connection has a certain strength, which basically determines how much one artificial neuron can influence another one.
So stronger connections equal bigger influence. Kind of like how we might value a close friend's opinion more than some random person on the street.
Perfect analogy. And in the perceptron, those synaptic strengths are represented by numbers. And here's the kicker. Those numbers, they change over time based on the perceptron's experiences. That, my friend, is the learning part.
Wait, so the perceptron is literally rewiring itself as it learns. That's insane. But how does it know what to change? Like, is somebody literally sitting there like, good job, strengthen that connection, or nope, wrong answer, weaken that one?
$1 million question right there. That was the heart of Rosenblatt's research. He had to create a set of rules, like a mathematical recipe, to guide the perceptron's learning. He called them reinforcement rules.
Reinforcement rules, huh? Sounds kind of like a robot parenting or something. So how do these rules actually work? What makes the perceptron, actually learn?
Okay, so imagine you're trying to teach this perceptron to recognize the letter A, right?
Okay.
So you show it a bunch of different A's, big ones, small ones, different fonts, maybe even some handwritten ones, just to mix it up.
Like visual flashcards for a robot brain.
Exactly. And every time it gets it right, every time it sees an A and it's like, yep, that's an A.
Uh-huh.
The connections between those artificial neurons that got activated, they get a little bit stronger.
So it's like those connections are becoming more sensitive to, like, the shapes and patterns that make up an A. But what about when it gets things wrong?
Well, that's where those reinforcement rules come in. If the perceptron sees, say, an H, right,
Yeah.
but it calls it an A, those connections that led to that wrong answer, they get weakened.
So it's not just about rewarding the good guesses. It's also about, like, pruning back the connections that lead to the bad ones.
Exactly. It's like pruning a tree, right? You
Yeah.
got to trim away the weak branches so the strong ones can really thrive. The perceptron is constantly fine-tuning, getting better at spotting those A patterns and ignoring the ones that just don't fit.
This is so wild. It seems so simple, but it's basically doing what our brains do, just with math instead of, actual neurons and chemicals.
It's pretty elegant, right? And it gets even cooler. Rosenblatt, he didn't just stop at one set of these reinforcement rules. He actually messed around with a bunch of different ways to adjust those connection strengths.
So different approaches to robot parenting depending on the perceptron's personality.
Something like that. Some were simple, some were way more complex, but they all came down to this. Reward the perceptron when it's right, discourage it when it's wrong, and let it figure out the patterns on its own. He even had some where the perceptron wasn't told when it messed up. It had to learn just from trying and failing.
Ooh, that sounds rough. Like, imagine learning to ride a bike, but nobody tells you how. You just keep falling off until you figure it out.
Yeah, trial and error, right, essential for learning. But the perceptron, since it's made of algorithms and not, flesh and blood,
Right.
it can take those spills a lot easier than we can. And that's actually one of the big advantages of having a model like this. You can run all sorts of crazy experiments that would be impossible, or at least really mean, to do with an actual brain.
So it's like a testing ground for different theories about how learning works, but without any of those, like, ethical dilemmas.
Exactly. And Rosenblatt, he really put this perceptron through its paces. He wanted to know, could it handle different types of learning environments? How well could it take what it learned and, apply it to new situations?
Okay, so this goes back to those ideal and differentiated environments he was talking about. What was that all about again?
Right. Okay, so remember how we were talking about how the brain might store information? That ideal environment, that's like that first theory where everything is just random. It's like the perceptron is trying to find patterns in pure chaos.
Good luck with that, perceptron.
Yeah, right, like trying to predict lottery numbers. But then there's the differentiated environment. That's where things get interesting. This is where the info actually has some structure to it, like those letters you were talking about.
So more like learning the alphabet from a children's book, where there's a pattern, a logic to it.
Exactly. And what Rosenblatt found is that in those more structured environments, the perceptron could actually start to generalize.
Meaning it could recognize a brand new A that it had never seen before, just because it had started to, like, grasp the underlying patterns of what makes an A an A.
You got it.
That's incredible. So even back in 1958, Rosenblatt was showing that a system, even a simple one, using math to, like, mimic the brain, could actually learn and adapt to new information.
It's pretty amazing,
It
really.
really is. It's like he kind of kicked open the door for this whole world of machine learning.
Absolutely. And remember, this was back when computers still used punch cards, for crying out loud.
Oh, man.
It just blows your mind to think what Rosenblatt could have done with the tech we have today.
Right. I mean, it's like he laid the foundation for, like, all of AI, starting with this relatively simple model. But how far can a model like this really go?
That's a question Rosenblatt himself wrestled with, actually.
Really?
Oh, yeah. He knew the perceptron had its limits, especially when you started talking about, like, abstract concepts.
Hey, so like what?
Well, things like understanding relationships, like bigger than, smaller than, that sort of thing.
Right.
Those were way beyond what it could handle.
So, like, recognizing a shape is one thing, but actually understanding what it means, that's a whole other story.
Exactly. And that gets to the heart of this debate that's still going on today. Can a machine really and truly understand what it learns? Or is it just like mimicking intelligence without any real comprehension?
Yeah, like, does the perceptron actually know what an A is? Or is he just really good at spotting a pattern?
$1 million question, right?
Yeah.
And Rosenblatt, to his credit, he doesn't pretend to have all the answers. In fact, he actually points this out in paper, this limitation, almost like he's saying, hey, I built this cool thing, but we still have so much to learn about how intelligence really works.
I like that. Recognizing the limits of your own work. It's just as important as, like, celebrating what it can do. But knowing what we know now about AI, I mean, it makes you wonder, what would Rosenblatt be working on if he were still around.
It's a trip to think about, right? Imagine showing him the latest in deep learning, these massive neural networks that can write music, hold a conversation.
Oh, man. Do you think he'd be surprised, or do you think he'd be like, yeah, I saw this coming back in 58?
I think he'd be blown away by how far things have come for sure. But I also think he'd see those core principles he was working with, the connections, the learning rules, the whole importance of structured information.
Yeah.
It's all still there at the heart of it all.
It's like he planted this seed back in 1958, and it's grown into this whole forest of AI research.
And what a forest it is, with so many paths still waiting to be explored. Because even with all the progress we've made, we're still a long way from truly understanding intelligence, whether it's the human brain or some fancy algorithm.
So what does all this mean for someone listening in, right? Someone who just took this deep dive with us into a paper from 1958. What's the takeaway?
I think the perceptron, it reminds us that even the most complex things, they often start with really simple principles. It's about understanding those principles, asking those big fundamental questions, and never being afraid to, push the boundaries of what we think is possible.
And on that note, I've got one last thought for you all out there to chew on. If learning, even in a machine, is all about strengthening and weakening these connections based on what it experiences, what does that say about how we learn best? What are those reinforcement rules that are shaping our own thoughts and perceptions every day?
Those are questions worth exploring.
Right. Maybe this little deep dive sparks some brand new questions for you. And hey, that's what we're here for, to spark some curiosity, ignite those imaginations, maybe even blow a few minds along the way. Until next time, happy learning, everybody.